All right, for our last lecture here, we have section 5 out of chapter 5. And you can see this is more integration. We're using this fundamental theorem of calculus. And I sort of talked about that a little bit in the last video. So I'm going to run down some examples, do a number of the homework problems, see how you're doing on this. Okay, okay. So definite integral, like I said, I kind of talked about this a little bit last time. Mainly the practical application is we're going to be able to find areas, find specific measurements inside. Now, they're going to start with this little word problem here. Daily cost function for a manufacturing firm. They give this equation right here. Remember our cost functions like we've done before. All right, so it looks something like this blue line right here. And they're going to say, what's the marginal cost? Now, if you recall marginal cost, we've done that a little bit. It's the derivative. So if you go back to this equation right here, the derivative of 180x plus 200 is simply 180. So the derivative is going to be this solid mark right here. All right. So now they want to know what's happening here, this area between 10 and 5. Now, I missed what they said that they're looking for. I guess they didn't lay this out in the problem. Apologies here. But if we're looking, oh, what's the difference here? Okay. Between 10 and 5. What's the difference of the cost functions right there? So you plug in 10, you plug in 5, you get the 900. That's essentially the difference of the two values. Okay. Now what they wanted you to show you was this area right here under the derivative is actually going to be the same 900. With the 5 height of 180, you multiply it, you get this 900. So we're kind of reverse engineering this here. What we're trying to say is that if you have any function and you want to find the area under the curve, you go back and you find the integral. You're going to go reverse of this, and it's going to give you some information, some answer. Okay, so that's where we're going right here. If you have a function right here and you take the integral of it, you're going to be able to find out what this amount is. You're going to be able to come up with that. So let me jump right to an actual real problem here. So we have this function, this cost function. All right. You see here, this is the graph, and it's a parabola, very wide parabola, but you're only seeing a portion of it right here. And same kind of thing. Again, we're going to go this direction. We want to find the marginal cost. And you have a couple problems like this. Anytime they see marginal cost, just go find the derivative. Simple as that. Okay. And now what they want you to find here is what's the area under this curve. All right. So we have a formula for this one right here. This is the negative 15x plus 305. That's what this blue line is right here. It's a downward curve. So they want to know this right here. Now, we can go back and do it, the previous version, but what I want you to see is that this is a trapezoid, and we've got a formula to figure this out. You can basically make a little triangle here and find that area, and then get this rectangle, add them up, and you'll find that using the geometric formulas, it's going to work when you have nice straight-edged shapes, like a trapezoid, like a square, or circles are exception. But it's not always going to be the case. All right. So what matters here, what we're going to use, is this fundamental theorem of calculus, where what it's saying is that if you have any kind of a integral right here, you integrate it. And when you have these definite integral, these two little points right here, this start and finish, what you're going to do is you're going to integrate it. You're going to plug in this top number to the answer. You're going to plug the bottom number into the answer, and you're going to subtract it. That's going to give you the amount that we're looking for, this antiderivative. All right, so I like to just get right into the examples, okay? The way I like to go, just see what we have here. We are first, no matter what these little numbers are, first job, when you see an integral sign and the dx, you need to integrate this function. Okay, so first thing, let's go find it. And they call it the antiderivative, whether you call it that or the integral, it's the same thing. So one at a time, all right? We're going to integrate this. So, and again, notice they always like to break this up into 3 integrals. You don't always have to do that. If you want to go right from here to the next step and integrate each of these one at a time, you can. So remember the rule. You increase the power of x by 1, that gives you a 3. You then divide by 3, divide by 3, and that's going to cancel this 3 right up front. That's why you're left with an x cubed. For this second term right here, the integral of EX is just EX. The negative 2 just sticks around. It's a constant out front. And the last one, we have the integral of something over X. Remember the 1 over X right here? You integrate that, you get a natural log of X. So we get X cubed minus 2EX plus 3 natural log of X. That's the integral of this original function. Now with in the past, we'd have this plus C, but now we don't worry about the C. We're going to plug in the 3 and the 1. So the answer we just obtained, or is it? I don't have, oh, it's right up here. I'm sorry. This is the integral that we found. And you don't have to write this capital F of X. Quite honestly, you can go right back to here. When you have this integral, I put that little slash of the 1, 3 last lecture. That's just saying take this answer and you plug the 1 and the 3 into it. So when you plug in 3 to this function right here, 3 cubed minus 2e to the third plus 3 times the natural log of 3, that's going to give you this negative 9.88. Then you plug in the 1 to this answer. You get 1 cubed minus 2e to the first plus 3 natural log of 1. That gives you a negative 4.44. And then remember, you subtract off that little answer. So when you subtract it, you basically get a negative 5.44. That's the answer we're looking for. Okay? So nothing, it's basically combining an old step with a little bit of algebra, plugging in some values. So here we're going to do the same thing. We're going to integrate this thing and we're going to find the definite integral from 0 to 1. Okay, so first off, remember, we learned U substitution a couple sections ago. Let's let that whole bottom be U. Then my du is going to be 2x in dx. In order to put a 2 here, I put that little half out front. That half is my compensator. So you recall how we did this? I need this 2 dx right here. I have the dx, so let's put a 2 here, and I can do that as long as I put a half out front. And what happens is my problem becomes a 1/2 1 over u du. Okay? And we're still going to integrate this like we always would. So you see in the next slide, that's what I had right there. You integrate it, you get 1/2 natural log of u. All right, now what's important, remember with the U substitution, you have to substitute it back. So my ultimate answer is this one right here, 1/2 natural log of 2x plus 4. Okay, it's not our final answer because now we need to go and get the definite integral. All right, so they say this, let the c equal 0. We don't even need to have the c anymore. All we have to do is take the answer, plug in the 1, plug in the 0, and that's what we get right here. So this is the format I prefer you do. Forget all this other stuff. You integrate it, you get your answer. Remember, we have this 1/2 natural log of 2x plus 4, and then you take these little numbers, these integration limits, they call them, and we're going to put these over to the side. Just a reminder, okay, now we plug in 1, then we plug in 0, and we subtract our answers, and that's what happens right here. 1/2 natural log of 1 times 2 plus 4, that's natural log of 6. Subtract what you get when you plug in 0, which is 1/2 natural log of 4. Then you calculate those, and you come up with this 0.203. And if you're not sure, let me just make sure everyone's on board with how I got that. Okay, so right here, natural log of 6. And then we divide that by 2 or multiply by half. That's what this front number would be right here. This would be a sorry, try that again. This would be a 0.896, I'll call it. Then we subtract what we get for the other one, so then we get natural log of 4, and we divide that by 2 or multiply by half, and that one becomes the 0.693. So remember, we're subtracting those. Now, in your calculator, we can do this here. I just subtract and add up a 0.896. You'll get your answer. Okay, that negative 0.203 they rounded up to. But if you're careful, you can do this on your calculator. If I do the natural log of 6 divided by 2, then I say equals, then I subtract the natural log of 4 divided by 2, and I'm going to get the same answer. You have to sort of cross your fingers a little bit and make sure you're good to go on this. So if you have any doubt of doing too many steps in your calculator, don't be afraid to do what I did right here. Maybe write another couple digits just to make sure, but you're going to get the correct answer. Okay, so that is an option that you have, and I just want to make sure you're clear how that actual part works. Okay, so now we have that answer, and now we're just doing another one of these. Oh, sorry, same problem. Oh, okay, I'm sorry. Different integration limits. Let's see here. Okay. This is one of these. It is an alternate way. So let me just cover this real quick. It's not necessary. We didn't really learn this when I learned calc, but we teach it because it is an alternate method if you're not sure with those numbers. So if I go back to the previous problem right here, okay, these integration limits are 0 and 1. They're x's because it's a dx. It's an x problem. All right. When I integrate, go back to this previous step. As soon as you integrate, remember the u substitution? You end up with this problem, and you get 1/2 natural log of u. Well, technically, where our problem is u's, we can't use the 0 and 1 from before because those are x values. When you switch to a u, you cannot use these numbers. So what we did was we substitute back to x, and then we plug this in. Now, what you're going to see here, this is an alternate way where you can actually do the u substitution, do all this, and now, remember we're integrating from 0 to 1? If you were to plug in x equals 0 to this equation right here, this u equals 2x plus 4, if you plug that 0 in there, you get u equals 4. So what it's saying is, in place of this x equals 0, we can replace that little number with a 4. Same thing when you take this 1, the old limit of 1, you could plug it into the u function and you get a 6. So what happens is, when you do the u substitution, you can actually go all the way here where we had that 1 over u, recall, and now we use these new integration limits, these 4s and 6s. And what's nice about this is, now I don't have to go and substitute back the x's. I'm done. At least I'm ready to roll. I have a u, I have a du problem, and I have these u limits. So that's what we can end up doing. And you see, we get natural log of u. Instead of substituting back the x's and using the 0, 1, let's just plug in 6 and 4. So we get 1/2 natural log 6 minus natural log 4. And you recall that was the same thing we had earlier. This just cuts one step out of the process. Now, some people like it because, like I said, it does save some steps. Some people absolutely hate it because it's a little more confusing. So this is where it's kind of your call. What do you want to do? What are you most comfortable with? And that's where I suggest just try them both out and see what you get. Now, if you go back to the original problem, what they're asking, recall, was here was our integral of this function between 0 and 1. So what it's saying is if you can graph that original function and you integrate from 0 to where 1 is, the integration number, this 0.203, that's the actual area under the curve. That's what we found right there. Okay? So look at another one of these here. And it kind of works backwards here where they tell you have maintenance costs and it's increase at a rate of m prime x. So they've given you the rate of increase. Okay? So they want a definite integral that represents a total maintenance cost from the end of the 2nd year to the end of the 7th year. So essentially, we're taking this function, we're integrating from 3 to 7. Now, why did they say 3 to 7? It's because I'm guessing that's end of the 2nd year to the end of the 7th year. Okay, I know why. End of the 2nd year, it's basically when year 3 begins all the way to the end of year 7. So it's years 3, 4, 5, 6, 7. That's where we're integrating from. Not exactly worded the best, but that's the idea they're looking for. If you were to graph this, the end of the 2nd year is basically at the number 3. The end of the 7th year is at the end of number 7. So that's why we're going from 3 to 7. But this is not a hard problem to integrate because now we have 90x squared plus 5,000. We integrate, remember, it's 30x cubed. Make sure you see how we got that. Increase the power by 1, divide by 3. That's why the 90 becomes 30. And then 5,000, it's a constant. Remember, when you integrate that, it's just a 5,000x. So now the integration is done. So notice there's no more integration sign. There's no more dx. This 7 and 3 is just a holdover so you don't forget what numbers you were integrating. I mean, you can always go back, but it's a way to remind you, oh yeah, we're not done. We don't put a plus c there. we're plugging in the 7 and the 3. So when you plug in 7 to this parenthesis, you get 45,290. When you plug in the 3, you get 15,810. Subtract them, and that's how we get our 29,480. Okay, that's a total accumulated cost. So it's like a running log of how much cost did we get in year 3, year 4, year 5, year 6, add them all up, and the total cost becomes this. And you see why an integral problem like this is effective in a business, because now we don't have to go and painstakingly add all these numbers. This just adds up the total cost of any time span you want. Okay, now they ask on this one, use a graphing calculator to estimate the value of the definite integral to 3 decimal places. Now remember, if you don't have a graphing calculator, obviously don't get one now. You can just use Desmos, desmos.com, and you can do the same kind of thing here. So what they want you to do is, it doesn't have an elementary antiderivative. Basically, at this point in your math, your calc careers, this is not one that you can actually integrate. But what you can do is you can plug stuff in. So there's a whole process in here of what you can do. You have an integration symbol, you plug in the 1.5, 4.3, you plug in the function dx, and voila, it just gives you your answer instantly. Okay, so why this is here, this is important because if you have a TI-84 or if you use Desmos, you use a tool because, I'll be honest with you, if you go into business, you're all in a business field while you're in this business calc class, odds are you're not going to remember all these integration formulas, but you have to remember that, oh yeah, it stands for this. It's going to tell me this area. It's going to give me some important data. How do I get it? Well, I don't want to go pull up my book and go figure this out again. You do have a shortcut calculator. Okay, very similar to how you learned your times tables. You learn how to add, subtract, divide, multiply big numbers when you're younger. Then you have a calculator which allows you to do that a lot faster without having to go through that painstaking process again and again. It's the same thing here. A graphing calculator will allow you to do some of these things in the future. Okay, so this is what you found. So if you go back, this function, x over natural log of x, looks like this blue graph. And then between 1.5 and 4.3, this is the area that we're finding right there. Okay, now your last important, what do you call it, definition or formula here is the definition of an average value. So this, when you integrate, you're getting the total money, total amount, total value that you spent, like that accumulated cost. If you want to find the average, well, you've got to parse it out. Because if you think about it this way, if you're a company and I want to know, okay, what was the total amount of money we spent on production in the last 2 years? Well, we can add that all up and get an accumulated cost. Okay, but if you say, well, what was the accumulated cost in the last 10 years, it's obviously going to be a lot bigger number, but it's not always good to compare 2 years versus 10 years. What do people always want to do? They want to find the average cost. Let's just go year by year. What was our average cost? So what you would do in that first case is, we'll take that total cost, divide it by 2 years. In the other scenario, take the total cost, divide it by 10 years, and in each case, you get your average yearly balance. This average value is similar. What it's saying is, by subtracting the B and the A, the span that we're going, the 2 years, the two values, you can then divide this out and you can figure out, well, how many years has passed? Let's divide the total we get by that, and that'll be the average value of a continuous function. So find the average value of this over the interval -3 over 2. Well, here's what we do. We're going to integrate it from -3 to 2, this function right here. Okay, so that's, if you just look at this right side, this is the normal part. This is the total value we're going to find over that span from -3 to 2. The new part is average value. So when you see average value, you got to think this formula. We find the difference of those. And remember, you take B, the bigger number, the n number, 2, subtract the first one. So it's a -3. That is a 5, 1/5. And that's how much time has spanned here in this interval. It's a total of 5 years. That's why it's 1/5 out in front. So we integrate, we have the 1/5. We integrate the 6x squared. So that's x cubed divided by 3. That becomes a 2 out front. This -2x integrated becomes a power of 2 divided by 2. And you're left with just minus x squared. So we plug in the 2. We plug in the 3. We subtract those values. And then we divide that by 15. So they didn't write this out, but let me just show you how that worked. Remember, when you're integrating, you're going to take this same function, plug in the 2, then plug in the -3, and we're subtracting those answers. So you see here we get 8, we get 16 minus 4. That becomes a 12 in that first parenthesis. Then over here we get -27, so that's a -54. And this is a +9, becomes a -9. So we're subtracting a -63, and that becomes a +75. Sorry, for this part. All of this right here is 75. Then we multiply by the 1/5, and that's how we get an average of 15. So what it's saying is, in that 5-year span, the total amount, the total value, the continuous total was 75, but we want to now break it down and say, what's the average per year? And so we divide it by 5. That tells us, yeah, it's about an average of 15 per year. That's what we get. Okay, so when they ask you for average value, this is the process that you're going to do. Okay, so in this particular case here, we have another supply question. Here's the supply. It's this exponential, this E function. Find the average price in dollars over the supply intervals 25 to 35. So what do? Average price, it's that same formula we just learned. We're going to integrate this function from A to B, from 25 to 35. And then we're going to divide by the difference. So I can already see the difference is 10. We're going to divide by 1/10. Or we're going to multiply by 1/10 or divide by 10. So we integrate all of this. Now, do you remember how to integrate an E function? Not so bad. See if you can figure out where this comes from. Just this part. Now, again, your PowerPoint slides are notorious for not always explaining where every value comes from. So I just want to talk about that real quick. So this is the integration that I'm dealing with. And I'll deal with the numbers in a second, but this right here. Okay, that's what we're integrating. So remember the rule. Well, right here, I'm going to substitute that. 0.05x, and this is a good time to review because we're having the final coming up. Take the du, the derivative. It's just 0.05 dx. So how does that work in our U substitution? Well, that means I need to have a 0.05 right up here to make this match. And how do I get rid of it? I put a 1 over 0.05 out front, so those blue things cancel off. So when I substitute everything in, this is an e to the u du, and I can pull that 10 out front. And then in your calculator, take 10 divided by 0.05, and I believe that's going to give us a 200 out here. And then, of course, the last part, or almost last part, is easy. The integral of EU is just simply EU. And then I substitute back the x that I just used in the U substitution, and we have this 0.05x. That is how they got all this right here. Okay, so like I said, I apologize, the slides don't always show all of that. They kind of make that assumption, well, if they've gotten to chapter 5.5, they know how to do everything before 5.5, but, you know, it doesn't hurt to see a review. So this is what we get, and then remember the next step is you plug in the 35, and you plug in the 25, and you subtract those answers. So this function that I just got right here, the one I have circled in blue, I plug in the 35. I plug in the 25 and I subtract them. And then the last step is, don't forget to divide it by 10. And that's where we get the $45.29 as our average price over the span. So think about what that means is, it's possible, you know, it's not like it was $45.29 every single year. It might have been looking something like this. And over time, the average is 45.29 or something like that. It may have been a lot less expensive in the beginning, kind of think of inflation, and then it got more expensive later. So maybe it started off at like $30. And then by the end of that 10-year span, it got up to $50, $60. The average price, though, if you break it down, is $45.29. So that's what's happening on that one. So now back to our homework problems like we always like to do here. Show you some of these and see what we have. Okay, somewhere in here, I think this is it. Yeah. So just want to go back and make sure you're all seeing the same thing that I'm hoping you're seeing here. If you get to your assignments, we've gotten all these quizzes and homeworks done. And just a reminder, remember, if you've already started homework 15, then do that one. I gave you a number of problems to skip. I put in the message board. I emailed you all. If you hadn't started it yet, we're on this better one, so that's the one I'm going to work on. We did these 4 last time, so let's just kind of pick up right there, and let's look at number 19. And the whole point here is I just want to make sure you all understand where I'm coming from each of these. Now, this first one, I'm going to tell you, this is probably one of the hardest ones just because of what they're asking you to do. But hopefully when you see me do this example, it won't be so bad. They want you to find the area under that function between the indicated values, -2 and +2. But they're saying use geometric formulas. Okay? So the first thing you got to know is, how does this graph look? Well, f of x equals √4 minus x squared, or y equals 4 minus x squared, essentially looks like this. It's a semicircle with a radius of 2. Sorry, I messed that up. Okay. A little bit better. So they want us to find this area right here under this curve. It goes from -2 to +2. Well, the way you can look at it as, if this is a full circle, I know the area of a full circle is pi r squared. And my radius is 2. So the area of the full circle is pi times 2 squared, which is essentially 4 pi. But since this is a semicircle, this is a circle right here. Semicircle, the formula is not anything that unique or memorable. It's simply 1/2. Sorry, let me write this again. Little tech trouble, apologies. 1/2 pi r squared. So you just plug everything in, you get pi times 2 squared, 4 pi divided by 2, your area is going to be 2 pi. That's our answer that we have right here. Now, one last thing. If you want to get the decimal area, you can always plug in pi to your calculator, multiply it by 2, and get that 6.28. But notice they want an exact answer, meaning they want to have that pi in there. No decimals, no rounding, and that's why that's the answer. If you were to put 6.28 in here, you're going to get it wrong. And this is, again, where the instructions come in. Make sure you answer the question the way they ask for. Okay, so let's look at number 23. Now we get to our normal integrals. We're integrating from 1 to 2 of the function 3x dx. So get you used to this process here. First, we just integrate this right here. The rule was you up your power by 1, divide by 2, and that's it for your integral. Now we're going to integrate from 1 to 2. So then the process is, remember, I'm going to use these big brackets. You don't have to use these, but we're going to plug in the 2 to this first one. Then we're plugging 1 into the second one, and then we are subtracting the answers we get. So when I plug in 2, and of course, you're doing this in your head or you're not writing all these steps, that's perfectly fine. I just want to show you each how we're getting it. In this first bracket, 2 squared is 4, 4 times 3 is 12, 12 divided by 2, we get a 6. In the second one, we get 3 times 1 squared, which is 3 times 1 over that, we get 3 halves. And now you just have to be able to do your fractions. We get 12 over 2, common denominator, minus 3 over 2. There's your 9 halves. And notice again, they want an integer or a simplified fraction. When they say that, that means don't give me 4.5. Okay, now I'm going to plug in 4.5. Sometimes if it's a decimal, I know if it's a decimal that you round, it goes on forever and you round it, you're going to get it wrong. Here, if I plug in 4.5, I might get it right. And it did. But that's only because it's a decimal that terminates, it ends. If you take 9 divided by 2 in your calculator, it's going to stop there. But if it's a decimal that goes 9.344444 and you cut it off and you round it, it's not going to give you credit here. The simplest way is when they say integer or simplified fraction, put in the 9/2. Put in the fraction we have, and it's going to work. Okay? So let's look at number 27. This is a section where it's really just practice, practice, practice. That's why you get a lot of these, because you'll figure out the trick, you'll figure out the trend, and like I've said a few times, the idea with this is the calculus is not difficult. It's always the algebra that you have to fall back on. You got to do that right. Okay, so in this problem, still have to integrate, so I'm going to rewrite this as 9x to the negative 2. So again, what it was when you have an x, a power on the bottom. So now I integrate it. Remember the rule. Add 1 to the power, which makes it negative 1. Then divide by negative 1. And now we get negative 9 over x is what we're integrating from 9 to 8. So plug in the 9 first. Plug in the 8 next. Notice this is my answer. This is my function, and I plug in my numbers in place of all the x's. And so we get a negative 1 plus a 9/8. And I'm going to get that common denominator again. And we end up with 1/8. That's my answer right there. So again, I could take that into a calculator, and I'm going to get the 0.125. And it should work, but let's just do the fraction, get used to that, and hopefully that's it, and there's our answer. So like always, pause if you need to look at this a little more. Not, when you're ready, play it, and let's move on. Okay, so number 31. I just like to rewrite these a little larger, so that's why you see me write it here in the middle of the top of the screen here. We're integrating from 0 to 1, and the function is 4x cubed plus 7 dx. So remember, no matter what those little numbers are, your first step is just to integrate. So the 4x cubed, the power goes up by 1, we divide by 4. Anytime you have a constant, you just put an x there. And now I can clean this up a little bit. We have x to the 4th plus 7x. We're integrating from 0 to 1, so I get 1 to the 4th plus 7 times 1 minus 0 to the 4th plus 7 times 0. And someone's going to ask me, well, do I need to write that next parenthesis because I know it's a 0? Technically, no. All right? I want you to be sure, though, that you know that this is all going to become a 0 because of that. But always consider it. Well, what happens when I plug it in? If you're seeing it's a 0, you don't need to do any more. You don't have to write that out. Oops, sorry. 1 plus 7. And my final answer should be a nice 8. Okay, so look that over. Make sure you're seeing how we got that answer. Again, they want an exact answer, so no decimal, but this is a whole number anyway, so it doesn't matter. And there's the result for number 31. Okay, so these are all pretty much the same ideas. I'm looking at them, and you'll see here on number 35 how we can do something a little different. We have the integral from 0 to 1. And notice these numbers are going to change. They happen to be the same sometimes, but they're going to vary. Doesn't really matter how you do the problem. It's just about how you plug, whatever numbers you plug in, you still have to do the integration correctly. So this is x to the 1/7. Don't forget what a root was. Now, the next part here, I'm going to tell you, does trip people up at times. When you add 1 to 1/7, now I'm going to do this off to the side here. I'll do it in blue so you see what I'm doing. We're adding 1 to 1/7. That's the whole step of integration, basic integration. Add 1 to the power. So that becomes 1 plus 7 over 7, and we get 8/7. So I just wanted everyone to see, where in the world did you get the 8/7? That's how I got it right there. Okay? Now, the other part of an integration is you add 1 to the power, and then you divide by the new power. So I'm dividing by 8/7, or it's the same as multiplying by the reciprocal. Same exact thing. So I have 49 over 8 x to the 8 sevenths. So if you're not clear what x to the 8 sevenths is, I'll again put this off to the side. X to the 8 sevenths is the 7th root of x to the 8th. That's what I'm plugging in. Now, the good news is we're only going from zeros and ones. So we get 49 over 8. Plug in the 1. Well, 1 to the 8 sevenths. Just look at this over here. 1 to the 8th is 1. The 7th root of 1 is 1. That's it right there. On the other part, plug in the 0. Well, 0 to the 8 sevenths is 0 to the 8th, which is 0. The 7th root of 0 is 0. So that becomes a 0. That whole thing is pretty much canceled off. And we're left with just 49 over 8. That's not a negative. That was just a scratch. So there's our answer on this one. Again, exact answer. Now, this one, what I wanted to show you earlier. Pretend I'm a calculator person, and I say, okay, I got 49 over 8. When I divide this, you're going to get 6.125. Oh, yeah. And this one does come out to be, I forgot, we're dividing by 8. It does come out to be a nice, clean decimal. So as you saw, if the decimal ends, you could put in that 6.125. My advice, just get used to plugging in these fractions. I know you may not like fractions, but plug those in, and now you're guaranteed to get your answer if you've done the steps right. Okay, let's look at number 39. All right, now the problems, as you see, they're going to get a little larger. They're going to draw on your previous knowledge, the stuff from this chapter, so you have to kind of make sure you juggle this correctly. So we're integrating from 1 to 3 of x e to the negative x squared dx. Okay, so how I see this one going is, I'm going to do a u substitution for everything in that power. That means my du is negative 2x dx. So if you look what I need negative 2x dx. Well, I got the dx, I got the x, I got to put a negative 2 here, and to compensate, I have to put a negative 1/2 out front. So now I have everything I need for the du. So when I substitute now, we get negative 1/2 integral of e to the u du. So once again, take a second, look at that, make sure you haven't forgotten how to do the u substitution, and you understand what I did here. That's always the hard part. Now the easy part is the integration, because all you do is you just get negative 1/2 e to the u. So we substitute back e to the negative x squared, and now we're going to integrate from, 1 to 3. So negative 1/2 e to the negative 9 minus negative 1/2 e to the negative 1. And now, like I always say, it's just some algebra. Let's clean this up a little bit and see what we get here. We get a negative 1/2. Oh, and they do want you to put, before I go any further, they say it's okay to do the decimals, 3 decimal places. So my recommendation is, let me just do a little cleaning up, and then we're going to plug this into our calculator. And I'd say go 4 or 5 decimal places when you write the answer, just in case. And then you can always round it at the end. So this becomes positive 1/2 e to the negative 1. For everyone see what we got as our answer. Now we're going to use that calculator if I can find it. There it is. And we're going to plug these pieces in here. Okay, so let's do one at a time. E to the negative 9. So in case you forgot, to find e to the negative 9, let's get the 9, hit that plus minus. Now we have a negative 9. Here's the e. We're going to divide that by 2. And then remember, it's a negative, so that's why this is a negative right here. And it's a tiny number. Okay? And I went 7 decimals just because I wanted to have something to show for this one. On the other one, same thing. Let's find negative e to the negative 1. We get that. Divide that by 2. And this is going to be a positive, so we have this positive 0.1 0.1839397. So all I have to do is just take that answer, subtract what I already found, 0.0000617. It's not going to make a much of a difference. But we get 0.183. I'll round that to 0.184. And there's our answer. I lost my calculator, but here's what we have there. And that's that one. Okay, so there's that one. Let's look at number 43. Forget how high this goes up to. Okay, so same kind of thing here. We have this integral. And like I said, I'm hoping the idea is that you do enough of these, you start to get the pattern. You start to see that there's just a series of steps that you're doing every time that's the same. So we're integrating from 4 to 5 of the function x square root of x squared minus 16 dx. Okay, so I'm going to do, like earlier, if you forgot, we're doing the u substitution where I'm going to let u be the inside piece. So du equals 2x dx. Okay, so remember what that means. It means we have to have 2x dx to make this problem work. Here's the dx, here's the x, I just need that 2. So I put the 2 there, and as long as I put a compensating fraction or something that cancels it off, I'm good. So now everything should be able to be replaced. We have, technically we shouldn't write the 4 and the 5 there because we're going to u substitution. But what we have left is just square root of u du. What matters is get the integration right. So we get 1/2. Remember, this becomes u to the 3/2. Okay, again, I added 1 to that power. And then when you divide by the 3/2, it's essentially like multiplying by its reciprocal. So this becomes 1/3. And now I'll substitute back the x's, x squared minus 16 to the 3/2. This is what we're going to integrate from 4 to 5. Now, as these problems get larger like this one, the suggestion I'm going to say is write out more steps. Don't try to do this in your head. Let's get it right. So remember what the process is. We are going to plug in. We're going to plug in that 4 right here, or the 5 right here. We're going to plug in the 4 right there into the answer that I just attained. So we have 1/3. 25 minus 16 to the 3/2 power. Over here, we have 1/3, 16 minus 16 to the 3/2 power. Now I'm going to focus on this other one on the right. You see how easy that becomes? It's 16 minus 16, we get a 0, that whole thing goes away. So that's a benefit. Doesn't always happen. As you see here, we have 9 to the 3/2 power. So if you forgot what that meant, again, that means the square root of 9 to the 3rd power. Now, whether that 3 is on the inside or the outside, it doesn't matter. I actually prefer it on the outside because it keeps our numbers a little bit better. So we now have 27 over 3. And after all that, we're left with just a nice little 9. Now, assuming we did everything right, plug it in, and there's our answer. Okay? So again, take a second to look at it if you need. And let's look at number 47. Oh, I guess there is no 47. That's pretty much it here. Let me close this and show you where I'm going next. Yeah, we've done all our problems for the homework, so we're good to go. I'm going to record another video in a couple days talking about the final exam. If you've already seen, there's a practice final exam, which is a good one. It's not required. It's not part of your grade. It's just for you to get a little bit of a look at what you can expect for the final exam. So, what I would say is, if you look in your assignments, where are they at? Right here. It's large, but it's a practice of the final. So if you were to click into it and you see, and it's going to say, okay, it's to allow you to simulate like you're taking a test. Now remember, it does not count. It's practice. So go ahead and start it. And I do have that set up where you should be able to take it multiple times. There's 150 questions here. Okay, so let me tell you. Number one, your final does not have 150 questions. This is just a big pool of questions for you to practice in, and they're randomized. So what I would say is, you do your problems and you do the next one, you do the next one. They're all mixed up. It's just to give you practice. So if you only get to do 5 of these, that's something. You do 20 of them, that's something. It's going to make you that much stronger when you're doing the problems. Or you can just scan them like I'm doing and say, okay, look, I know how to do that one. I don't need to do it. I'll skip it. Or you get to this one. Well, I forgot how to do this one. Let me go review it. Let me try it. Now you're not going to get immediate feedback like your homework where you can say, oh, show me a similar problem, or oops, got it wrong, do it again. It's going to be like a test, so you submit it. So it's a way for you to simulate how your test is going to be. And then in the end, when you're done, it's like, okay, I'm going to submit this, and it'll take all the ones that you did, and it's going to tell you what you did right or wrong. And you can click on it, and it's going to tell you what the answer was, and it'll tell you what you put in. Like, I didn't do anything on here, but at least you can see the answers. So don't feel like, oh, I got to do this whole thing, and I can't submit it to the end. Go ahead and submit it, and what you now have is you have essentially a list of 150 questions with the answers. Okay, it's not the same ones as your homework or your actual final, but they're close, just to give you a little preview of what's going on. So it's a great resource. Obviously, your priority is going to be this quiz, which is still due on Monday. So get that quiz done. Don't just skip that. And then the final exam is going to appear, the actual one that counts. It's going to appear on Friday morning this week, the 6th, and it is due on the evening of the 13th, Friday the 13th. So you can't forget that one. Friday the 13th is when your final's due. Make sure you get it done. You only get one try. And important thing, it's like a quiz, or it's like a test. It is a test. Once you start it, the clock is running. So you see how I'll show you again on this one. It's going to ask you the similar question. When you click start, the timer works. Now, I don't think I put a timer on the practice final, but your actual final is going to have a timer. It's a few hours. It's plenty of time, but the clock runs. So if you close the window and then you leave and come back later, the clock continues to run. So if I forget what it is, if it's a 3-hour window, you started at noon and you say, okay, I'm going to pause and come back at 2, you have an hour left. If you come back at 4, the final is over for you. It's going to submit what you had. So the clock, as soon as you say, go ahead and start it, the clock starts for you, and that's your only shot at it. So you can't come back and try it again. You can't, have it reset. It begins right there. Okay, so that's it for this one. Like I said, I'll record another video kind of talking more about the final. But you should be good to go. If you have any questions, shoot me an email like always, and I'll see what I can do to help you out. All right, good luck. Have a good one.